You know that feeling, right? When you finally get your hands on a really powerful tool, like a large language model, maybe a GPT-4 or Llama 3, but then you realize it needs like hours, maybe even days of specialized training just to do your specific thing. It feels a bit like having a supercar, but then needing to spend a whole week in the garage just to figure out how to change the radio station. Well, today we're taking a deep dive into a really revolutionary approach that aims to solve exactly that problem for LLMs. We're going to unpack a fascinating paper. It's titled Drag-and-Drop LLMs, Zero-Shot Prompt to Weights.
Yeah, and this deep dive, it's really about exploring how we can potentially move beyond that traditional, often very time-consuming fine-tuning process. Think of it as a detailed exploration through some pretty groundbreaking research. We're going to structure it much like the paper itself, actually. The goal is to help you really grasp the core concepts, the methodology they used, and the pretty profound implications this has for customizing AI. Our mission here is to pull out the most important insight so you walk away feeling truly well-informed.
Okay, let's get into it. To really appreciate what drag-and-drop LLMs, or D&D as they call it, actually achieves, we probably need to understand the landscape it's trying to disrupt first.
Right. And what's fascinating here is starting with the basics of LLMs themselves. These models, like you mentioned, GPT-4, Llama, maybe Qwen 2.5, they're pre-trained on just enormous amounts of internet data. And this pre-training gives them what's called zero-shot competence. Basically, the ability to do tasks they haven't explicitly seen examples of before, things like math, coding, or even complex reasoning.
But often you, our listener, might need something more specific, right? Like task-specific behavior, maybe something tailored to your company's internal documents, or a very unique response style. Historically, getting that specificity means fine-tuning.
Exactly. And that's where techniques like parameter-efficient fine-tuning, or PEFT, come into the picture. Methods like LoRA, for instance. LoRA is clever because it reduces the computational cost. It only tunes a small set of additional parameters, keeping the massive original model weights frozen. But, and this is the catch, there's still the wall clock cost, the actual time it takes. Adapting even a, let's say, 0.5 billion parameter Qwen 2.5 model with LoRA that can still take something like 4 A100 GPUs for half a day.
Half a day with 4 powerful GPUs, just for one task adaptation.
Yeah. And that becomes a really significant computational bottleneck at massive scales. Because think about it, each new task, or maybe each new user needing customization, requires its own separate optimization run, its own training session.
Okay, so even PFT, which is efficient in terms of how many parameters you change, still requires dedicated, sometimes lengthy training for every single new use case.
Yeah.
That definitely sounds like a hurdle for, say, dynamic, widespread AI customization.
Precisely. And, prior research did look into parameter generation, trying to create weights directly, often using things called hypernetworks, basically networks that generate weights for other networks. But these earlier attempts often struggled. They tended to either ignore task conditioning or use simple binary embeddings, which means they couldn't really deeply tailor the models to diverse, nuanced tasks based on, say, natural language descriptions. The core idea, the real insight behind D&D, comes from this observation. A LoRA adapter, those small added parameters, is fundamentally nothing more than a function of its training data.
Ah, okay. So the specific data used to train it determines what those LoRA weights become.
Exactly. So the paper asks, what if we can learn the mapping directly from prompts to weights? If we could do that, they argue, we could potentially bypass gradient descent altogether. That's the big leap, skipping the iterative training process entirely.
So the drag-and-drop name isn't just catchy marketing. It really signifies a fundamental shift. A simple, tuning-free process that directly generates task-specific weights.
What were the specific, the biggest hurdles the researchers were trying to overcome with this new approach?
Yeah, the paper lays out 3 main challenges pretty clearly that D&D was designed to tackle. First, how do you equip the parameter generator with, an effective drag-and-drop ability?
Yeah.
How do you make it robust for adapting these complex LLMs? Second, can you actually achieve this adaptation without task-specific training, but while maintaining performance that's comparable or maybe even better than traditional tuning? And third, how do you make this whole thing user-friendly and accessible, something that really lives up to that intuitive drag-and-drop idea?
That does sound ambitious, almost too good to be true in a way. So how exactly does D&D manage to pull off this drag-and-drop magic? What's the architecture? What's under the hood? All right, so the architecture is really quite ingeniously designed. The whole point is to establish a direct learnable connection between a task description given as a set of prompts and the specific LoRA parameters needed to make the base LLM good at that task.
Okay, so how does it get started? What's the very first step in preparing the system to even learn this kind of mapping?
The first crucial step is what they call data preparation.
Yeah.
And this involves first collecting a bunch of LoRA adapters. These adapters are pre-trained on a really diverse set of data sets, and they save checkpoints at various points during that training. These saved weights become the ground truth parameters the system needs to learn to generate. Then, they take unlabeled data samples, just the prompts, from those same training data sets. These prompts act as fingerprints, or representative proxies, for their respective tasks.
Fingerprints, okay, like a signature for the task hidden in the input example.
Ooh. Exactly. And then comes the key part, prompt checkpoint pairing. They randomly pair batches of these prompts with randomly selected LoRA checkpoints that were trained on the same data set the prompts came from. These pairs, prompt batch corresponding LoRA checkpoint, form the input supervision data for the generator. This is absolutely fundamental for teaching the system that data parameter mapping, learning how a certain kind of prompt relates to a certain set of LoRA weights.
Got it. So you're basically showing the system, when you see prompts that look like this, the model adjustment should look like that. What happens to those prompts next? How does the system read them?
Right, so next up is prompt embedding. They use a lightweight text encoder. The default they mention is SentenceBERT, which is a pretty standard tool for this. Its job is to take each batch of prompts and distill it down into condition embeddings. These are dense numerical vectors that capture the semantic meaning, the essence of the task described by the prompts. These embeddings are what will guide the parameter generation.
Okay, embeddings capture the task, meaning, and then the actual generation part. What's the brain of this operation, the thing that actually creates the LoRA weights?
That would be the parameter generator itself. Specifically, they use what's called a cascaded hyper-convolutional decoder. It sounds complex, but it's essentially a sophisticated neural network architecture. It uses layers of 2D convolutions designed carefully to transform those compact condition embeddings, the prompt fingerprints, into the full set of LoRA matrices, matching their required shapes and sizes. Its main job is just to expand that semantic information from the prompt embedding into the actual usable model parameters.
And how does this generator learn to do that accurately? How is it trained?
The learning objective, the way it learns, is actually remarkably straightforward. It's optimized using mean squared error, or MSE loss. Basically, it compares the parameters it generates to the target parameters, those original LoRA checkpoint weights they collected earlier. The system is trained to minimize the difference, the error, between its output and the ideal target weights. This pushes it to become highly accurate at synthesizing the desired parameters.
Makes sense. Train it to match the known good examples. So for us, the users, let's say I have a new task, a new data set. How does inference work then? What do I actually do?
It's incredibly simple at inference time. For your new data set, you just take a small sample of prompts from it, maybe just a handful. You run those prompts through the trained text encoder to get their condition embeddings. Then you feed those embeddings into the trained parameter generator, and poof, out come the LoRA parameters specifically generated for your new task. You plug those into your base LLM and evaluate. And the crucial part, this whole process takes seconds. No fine-tuning needed. The paper shows this works well both in-domain, like generating parameters for a new common-sense task when trained on other common-sense tasks, and even cross-domain, like using it for science tasks after training only on common sense. Shows its versatility.
All right, seconds instead of hours or days. That's the promise. So that's the ingenious setup. But, the proof is in the pudding. What about the results? Does D&D actually deliver?
Yeah, the experimental findings reported in the paper are, frankly, quite compelling. They really seem to validate the whole approach. They used Qwen 2.5 as their base LLM, a solid open-source model, and they tested D&D across a really diverse set of tasks: common sense reasoning, coding, math, even multimodal understanding involving images and text.
Okay, let's hit the big numbers first. Efficiency. Just how much faster are we talking?
The efficiency gains are, well, they're pretty staggering. D&D generates these task-specific parameters in seconds, right? Compared to traditional methods, this leads to massive overhead reduction. They report up to 12,000x lower overhead than full fine-tuning.
12,000 times.
It's also 2,500x faster than mild full-shot tuning, that's tuning on the full data set for a moderate number of steps, and even 12,000x more efficient than extended full-shot tuning.
Right.
And importantly, for situations where you only have a few examples, it outperforms fuse-shot tuning and in-context learning when you have fewer than, say, 256 examples, and it does this with almost negligible computational overhead.
Wow. Okay, that speed is just incredible. But the critical question, does it perform well? Did they have to sacrifice accuracy for that speed?
That's the key question, right? And the answer seems to be no, quite the opposite in many cases. The paper reports average gains up to 30% in performance over the strongest training LoRAs on unseen benchmarks. These are benchmarks for common sense, math, coding, multimodal tasks that the generator never saw during its own training. This is really crucial because it strongly suggests that D&D isn't just like memorizing the parameters it saw during training. Instead, it genuinely learns to establish data parameter mappings and can use that learned mapping to adapt the LLM effectively for truly novel data sets. It's learning a general skill.
Right. It's not just a lookup table. It's actually synthesizing appropriate parameters.
Yeah.
What about that cross-domain generalization you mentioned? That sounds incredibly important for real-world use, where tasks aren't always neatly in the same category it was trained on.
It is absolutely vital, and D&D showed robust cross-domain generalization despite never seeing the target data or labels. The example they highlight is transferring from common sense reasoning tasks, which it was trained on, to science benchmark tasks, which it wasn't, and it achieved an 8.7% accuracy improvement on those unseen science tasks compared to strong baselines. That really demonstrates its versatility across quite different knowledge domains.
That's impressive. Does this method hold up when you use bigger foundation models? Does it scale?
Good question. Yes, they found it scales well with larger foundation models, testing it from 0.5 billion up to 7 billion parameters. This is significant because many practical LLM deployments are in that 7B range or larger. It maintains strong performance even on really tough benchmarks like Live Code Bench. That's a benchmark specifically designed to test code generation in a realistic, evolving environment. There, it showed an average pass at one improvement of 20.3%. That means the first code attempt it generated was correct over 20% more often than the baseline. So yeah, it seems to scale effectively.
And could these D&D adapted models actually beat the original base LLMs at specific tasks?
Yes, in many evaluations, D&D outperforms foundation LLMs across all tasks.
Yep.
This really highlights its ability to generate genuinely superior task-specific parameters that provide a significant performance lift over even very capable base models.
Okay, and one last thing on results that drag and drop effect itself. Did they manage to visualize it somehow, show that the generated parameters are actually good?
They did. They included visualizations like TSNE plots, which basically map high-dimensional data, like model weights, into 2D space. These plots show that the parameters generated by D&D end up having a distribution that's close to original ones in the weight space, meaning they look similar to weights obtained through careful traditional fine-tuning. But what's even more striking is that these generated parameters sometimes achieve even superior performance than full-shot tuning. They give an example on the ARCC benchmark where D&D got 51.6% accuracy, while a standard full-shot tuned LoRA only got 40.7%. So that visual similarity combined with often better performance really brings that drag-and-drop effect instant, high-quality specialization to life.
Okay, so D&D works, and it seems to work incredibly well. Now, good research papers often include ablation studies. It's like carefully taking apart the engine piece by piece to see exactly what each part contributes, right? What did they learn from these ablations about the best way to actually build and train a D&D system for optimal performance?
Right, these ablation studies are super important for understanding why it works and which design choices really matter. They basically tested variations of the key components. So first, they looked at the condition type, what kind of information you feed in to represent the task. They found that using raw prompts, just the input examples, was the most effective, giving that 51.6% accuracy on ARCC we just mentioned. Interestingly, trying to use prompt plus answer combinations actually performed quite poorly for common sense reasoning, dropping accuracy way down to 27.0%.
Wait, adding the answers made it worse. Why?
Yeah, it seems counterintuitive, but for common sense tasks, the answers often lack diversity. Think multiple choice questions where the answer is just A, B, C, or D. Giving these simple answers as input can actually detriment data set specific representations. It doesn't provide rich enough information to distinguish tasks well. Now, they note that for tasks like math, where answers can be complex equations or proofs, using answers can sometimes work. But generally, just using the prompts alone is recommended because they usually contain richer semantic clues about the task itself.
Fascinating. Sometimes simpler is better for the conditioning signal. Okay, what about the condition extractor, the part that actually reads the prompts and turns them into those embeddings?
Yeah, the choice of the condition extractor definitely matters. Their default choice, Sentensberg, gave the best results at 51.6% again. But interestingly, even older, Traditional methods like love embeddings, which just represent words as vectors, still yielded pretty promising results, around 50.8%. So there's some flexibility there. However, trying to use much heavier decoder-only models, like using the Qwen 2.57b model itself as the extractor, performed poorly. Some even failed outright.
Why would using a powerful LLM as the extractor fail?
They suggest a couple of reasons. One is just computational cost. These big models are slow, which limits how many prompt parameter pairs you can process in each training iteration. This might restrict the generator's awareness of novel datasets because it sees fewer examples overall. Also, the specific architecture of these decoder-only models might constrain the kind of diverse condition representations needed. Lightweight encoders seem better suited for this specific job.
Okay, that makes sense. And the training data itself, the collection of datasets used to train the D&D generator, does quantity and diversity matter there?
Oh, absolutely. The training data arrangement, particularly its diversity, is critical. The results clearly show that more training datasets lead to better performance improvement. Why? Because it ensures better coverage of condition parameter correlations. The generator sees more varied examples of how prompts relate to weights across different domains. This diversity is key for making D&D robust when it encounters completely new, unseen tasks. And of course, you need a basic amount of training samples. If you try to train it on just one or two datasets, it just doesn't have enough information to learn that general mapping effectively.
Right. Diversity is key for generalization. And finally, how did they pair the prompts with the checkpoints during that initial training? Did the specific strategy matter?
Yes. The condition parameter pairing strategy turned out to be another vital piece. They compared two main strategies. Strategy 1 used the same fixed set of prompts for all the LoRA parameters from a given dataset. Strategy 2, instead, randomly picked different prompt batches from a larger pool of candidate prompts for each parameter checkpoint. Strategy 2, the random sampling from a larger pool, was found to be clearly superior.
Why was random pairing better?
It leads to improved model generality, convergence speed, and even memory consumption. Essentially, exposing the generator to more varied prompt combinations during training forces it to learn a more robust and general mapping. It again highlights that core theme. The diversity of training data in all its forms is absolutely crucial for equipping D&D with its powerful zero-shot drag-and-drop capability.
Okay, this deep dive has really shown us how D&D could dramatically change LLM customization, shifting it from, hours or days of fine-tuning to potentially just seconds of direct parameter generation. Stepping back a bit, where does this fit into the broader field of AI research, and what does it suggest might be next?
Yeah, connecting it to the bigger picture is important. D&D clearly builds upon the work in parameter-efficient fine-tuning, PEFT. It acknowledges that PEFTs significantly reduce the cost of tuning. But it directly addresses PET's main limitation, the fact that it still requires that per-task tuning step. D&D's whole contribution is about eliminating that per-task optimization altogether.
And how does it compare to those earlier attempts at parameter generation you mentioned?
That's a key distinction. As we touched on, previous work in parameter generation often struggled, especially with zero-shot ability on complex tasks. They might have worked okay in limited scenarios, but often failed when faced with entirely new, unseen data types or tasks. D&D's innovations, particularly using rich prompts as the condition and the specific pairing strategies during training, significantly boost its robustness and generality for novel datasets. The paper explicitly compares it to methods like RPG, noting that while RPG fails on open set generation, D&D still presents strong zero-shot ability. That ability to generalize to the unknown is really where D&D seems to shine.
So looking forward, what does this all mean for the future, especially as these language models just keep getting bigger and more complex?
Well, the paper itself poses this really interesting question. If we can start thinking of network parameters, the weights themselves, as a new form of data modality, something that can be generated just like text or images, what are the big future challenges for this whole emerging field of weights-based learning? They outline several critical directions. One is obviously scaling parameter generation to even larger models. Can this work effectively for models with 70 billion parameters or even more? That's a huge open question. Another is leveraging existing pre-trained checkpoints from the internet. There's a vast amount of trained model weights out there already. Can we use those somehow to train even better, more versatile parameter generators? And a third exciting direction is generating structurally diverse models. Could we use this approach to generate not just LoRA adapters, but maybe different model structures tailored for varied hardware configurations, like generating a model optimized for a specific phone chip?
Wow. Okay, so what we've really seen today with drag-and-drop LLMs feels like a genuinely transformative step. It's potentially a leap beyond that constant, often costly cycle of fine-tuning for every little thing. It offers this vision of instant, efficient, and highly generalizable specialization for large language models. It almost feels like AI learning how to adapt itself, much faster than before.
It really does. And it challenges a very long-held assumption in machine learning that gradient descent, that iterative optimization process, is absolutely indispensable for specializing a model. D&D proposes this exciting alternative paradigm. Instead of painstakingly training and adapting, we might be able to directly generate the precise parameters needed for a task, potentially in a single rapid forward pass. This could fundamentally change the relationship we have between data, the models themselves, and the whole optimization process.
It really makes you think, doesn't it? I mean, if we can literally drag and drop model intelligence onto new tasks in just seconds, what kinds of possibilities does that open up? Think about truly personalized AI systems, adaptable on the fly, in every field imaginable: healthcare, education, creative tools. The idea itself that the network parameters, the weights, can be a generative target, a new form of data modality, as the paper puts it. That's really provocative thought for you, our listener, to consider as AI just continues to evolve at this incredible pace.